Thermal imaging operates differently from traditional cameras. Instead of detecting reflected visible light, it senses heat energy emitted by objects. This allows detection even in complete darkness where conventional optics fail. At night, visible light cameras struggle to capture meaningful detail. Without illumination, the environment appears nearly black, and objects blend into shadows. Human vision and standard sensors rely on reflected light, which is often unavailable in low-light conditions. Thermal imaging overcomes this limitation by revealing temperature differences. Warm objects stand out clearly against cooler backgrounds. The human body naturally emits heat, making it visible even when hidden in darkness. All objects emit infrared radiation, depending on their temperature. Warmer surfaces radiate more energy, while cooler areas emit less. Thermal imaging systems measure these variations to create a temperature-based visual representation. A specialized lens collects infrared radiation from the scene. Unlike traditional glass optics, thermal systems often use materials designed to transmit infrared wavelengths efficiently. This focused energy is directed toward the internal sensor. Infrared radiation passes through the optical assembly and converges onto the detector surface. The optical design ensures that heat energy from different parts of the scene is accurately mapped onto corresponding sensor locations. Inside the camera, a microbolometer sensor array measures tiny temperature differences. Each individual pixel responds to small variations in heat energy. Even minimal differences between objects become detectable. Every pixel in the sensor records the temperature of a small portion of the scene. Warmer areas generate stronger signals, while cooler regions produce weaker responses. Together, these readings form a thermal map. Electronic processing circuits convert raw temperature data into a visual image. The system assigns brightness levels or gradients to different temperatures, transforming invisible heat into a visible display. Warmer objects appear brighter than their surroundings. Cooler terrain appears darker. This contrast allows operators to quickly identify people, vehicles, or equipment based on heat signatures. Different materials emit heat differently. A vehicle engine retains warmth, vegetation cools quickly, and terrain changes temperature slowly. These variations produce unique thermal signatures. Warm machinery is especially easy to detect. Even after a vehicle stops moving, the engine block and exhaust components remain hotter than the surrounding air. Thermal cameras highlight these differences clearly. Heat traces can also remain temporarily on surfaces. Footprints left on cooler ground may appear warmer for a short period before dissipating. This allows detection of recent movement. Moving targets are often easier to detect. As a person or vehicle moves, the heat signature shifts against the background, creating dynamic contrast that stands out to observers. A wide thermal view reveals multiple hidden heat sources simultaneously. Humans, vehicles, and infrastructure all emit heat, allowing detection even in low visibility environments. Thermal imaging can detect targets through light vegetation. Leaves and thin branches may partially obscure the view, but body heat still radiates through gaps, revealing silhouettes. Some materials reduce thermal visibility. Thick walls or insulated barriers absorb or block heat radiation, decreasing contrast and making detection more difficult. Recently operated engines remain warm after shutdown. Thermal cameras can identify vehicles that were active minutes earlier, even if they are no longer moving. Buildings also emit heat. Ventilation systems, rooftops, and windows may radiate warmth at night, creating distinct patterns visible in thermal imagery. Animals can be detected in darkness using thermal imaging. Their body temperature contrasts with cooler surroundings, allowing identification even in dense terrain. Long-range thermal optics enable detection at distance. High-quality sensors and optics maintain clarity while observing heat signatures far from the camera position. Higher-resolution sensors improve detection accuracy. Smaller pixels allow finer temperature distinctions, revealing more detail within the thermal scene. Terrain stores heat during the day and releases it slowly at night. Rocks, soil, and structures cool at different rates, producing complex thermal backgrounds. When objects share similar temperatures, contrast decreases. A person near a warm surface may blend partially with the background, making detection more challenging. Overall, thermal imaging reveals heat differences across the entire scene. By sensing infrared radiation, these systems provide visibility independent of lighting conditions.
Thermal cameras can scan large areas quickly, identifying multiple heat signatures across wide terrain. By sweeping the field of view, operators can locate warm objects that contrast against cooler surroundings. To maintain accuracy, thermal sensors must remain stable. Internal calibration systems regulate sensor temperature, ensuring consistent readings and preventing drift during long observation periods. Warm targets become highly visible in cold environments. A human body standing in cool terrain produces strong thermal contrast, making detection easier even at significant distance. Vehicles generate distinctive thermal patterns while moving. Engine heat, tire friction, and exhaust components create identifiable signatures that stand out from cooler ground. Elevated viewing positions improve detection coverage. From higher vantage points, thermal cameras observe broader terrain and identify targets across larger areas. Partial cover does not fully conceal heat. A person behind thin obstacles may still emit detectable infrared radiation visible to the sensor. Thermal imaging operates independently of visible light. Whether day or night, the system relies on temperature differences rather than illumination. Residual heat left behind gradually fades. Recently disturbed surfaces cool over time, reducing visibility of previous movement. Clothing influences thermal visibility. Insulated garments reduce heat emission, while thinner materials allow body heat to radiate more clearly. Thermal imaging reveals hidden targets by emphasizing temperature differences. Even subtle variations become visible when contrast is sufficient. Stationary targets still emit heat. A person lying still on cooler terrain remains detectable due to body temperature. Equipment continues emitting heat after use. Recently powered devices remain warmer than surroundings, allowing detection even when inactive. Thermal imaging is commonly deployed from aerial platforms. Drones and aircraft use elevated sensors to monitor large areas efficiently. Detection range depends on heat contrast. Greater temperature differences allow longer range identification, while similar temperatures reduce visibility. Sensitivity adjustments enhance detection. By tuning gain and contrast, operators can emphasize small temperature differences. Terrain cover may reduce but not eliminate detection. Heat may still radiate from partially concealed targets. Heat traces disappear gradually as surfaces cool. Thermal signatures from movement become less visible over time. Thermal systems track multiple targets simultaneously. Each heat source appears independently within the scene. Infrared energy is continuously measured by the sensor array. Real-time updates maintain an accurate thermal picture. Thermal imaging detects targets based on temperature contrast rather than shape alone. Even unusual silhouettes remain visible. Environmental temperature strongly affects performance. Warmer surroundings reduce contrast between targets and background. Sun-heated surfaces store warmth and release it slowly. Buildings and terrain may remain warm after sunset. Similar temperatures reduce visibility. When target and background share similar heat levels, detection becomes more difficult. Moving targets remain easier to identify. Motion combined with heat contrast improves recognition. Thermal systems can track several heat sources simultaneously across wide terrain.
Thermal sensors update temperature readings continuously. Each frame reflects the latest heat distribution across the scene. Complex environments, such as forests, still allow detection. Heat signatures remain visible through gaps in vegetation. Elevated sensors increase detection range. Higher positions reduce obstruction and expand coverage. Cooler environments improve detection. Lower background temperature increases contrast with warm targets. Thermal imaging relies on temperature contrast to distinguish objects. Greater differences produce clearer images. Continuous scanning helps locate heat sources. Operators sweep terrain to identify new targets. Infrared lenses focus heat energy onto the sensor. Optical systems ensure accurate mapping. Each sensor pixel measures temperature differences. Combined readings create a full thermal image. Moving heat sources update instantly. Targets remain tracked as they change position. Multiple heat sources appear in a single scene. Humans, vehicles, and structures remain visible simultaneously. Partial concealment still leaves thermal signature. Heat escapes around obstacles. Heat signatures fade as objects cool. Recently active equipment gradually blends into background. Optical zoom improves distant detection. Magnification maintains visibility of heat sources. Aerial thermal imaging expands coverage area. Drone platforms monitor wide regions efficiently. Thermal imaging detects targets using temperature differences across terrain. Elevated thermal systems monitor large areas continuously. Wide coverage improves situational awareness. Automatic gain control enhances visibility. The system adjusts contrast dynamically. Clothing influences thermal appearance. Insulation changes heat emission. Moving vehicles produce dynamic heat patterns. Engine and friction generate detectable warmth. Thermal imaging works in complex environments. Targets remain visible despite clutter. Residual heat fades over time. Recently disturbed surfaces cool gradually. Microbolometer sensors detect infrared radiation precisely. Tiny changes become measurable. Optical magnification improves long-range detection. Distant targets remain visible. Thermal imaging identifies multiple targets simultaneously. Each heat source is tracked independently. Thermal imaging ultimately detects targets using temperature contrast, enabling visibility regardless of lighting conditions.